friends, welcome back to this online certification course on watershed hydrology. I am Rajendra Singh, professor in the Department of Agriculture and Food Engineering at Indian Institute of Technology, Kharagpur. We are in module 2. This is lecture number 3 and the topic is evapotranspiration. And this lecture will introduce evapotranspiration, will have a look at transpiration and its measurement. We will talk about factors affecting evapotranspiration. We will then go into measurement of evapotranspiration, and then we will talk about evapotranspiration determination using hydrometeorological equations. Let us start with evapotranspiration. So, if remember hydrological cycle which we introduced in earlier classes. So, obviously, we know evaporation occurs from water bodies and that is how the water is transferred from land to atmospheric system, and also transpiration occurs from the canopies of trees or plants or crops, and that is transpiration. So, evapotranspiration is sum of evaporation and transpiration, that is it is a combination of two processes, evaporation and transpiration, where evaporation is loss of water from the soil surface or water bodies, that it can be from mainly from water bodies, but even if it is a irrigated lands or soil, saturated soil, then from there also evaporation will take place, and then transpiration, which is loss of water through plant leaves. So, this combination of these two is known as evapotranspiration. If you look into evapotranspiration sub-processes, then we know that evapotranspiration is sum of evaporation and transpiration. Transpiration of course takes from plants or crops or whatever, and evaporation occurs, it could occur from open water bodies, from soil, and from also vegetation surfaces. That means, we saw that when rainfall occurs, a part of that is intercepted by plants and buildings or other abstract objects. So, obviously, from the vegetation surfaces also evaporation will take place, so is from buildings. Now, let us talk about transpiration first. So, evaporation already we have discussed. Now, we talk about transpiration here. It is a process by which plants utilize water for their metabolism and growth. So, we have already read in our junior science classes that root system extracts water from the soil and stomata in leaves transpire it. So, basically the roots extract water and nutrients from the soil, then through stems it reaches leaves. It is used by plants for their growth and metabolic activities, and of course, the stomata which are there on plant leaves, through which this water transpires. Similar to evaporation, except that water escapes from plant leaves rather than the free water surface. So, basically process wise it is more or less similar, but in that case evaporation case we saw that it could take from water bodies or from soil also, as we discussed, but in this case it is exclusively limited to the plant leaves. Now, coming to measurement of transpiration, it is measured using an equipment called phytometer, which is basically a large vessel filled with soil in which plants are rooted. So, basically it is a large vessel. Sometimes it could have the measurement facilities. Basically, when we say measurement, is basically they could be of weighing type, that some kind of weight measurement is possible. And in this case what happens is soil surface is sealed to prevent evaporation, so that only moisture escape is by transpiration. So, what happens that we put the plants in this soil, will irrigate, and then what we do, we seal the surface completely. So, that simply means what, that we are stopping or checking the evaporation taking place from this vessel. So, only loss of water that could take place is through transpiration, that means through plant system. And the lost moisture can be determined by weighing the plant and container before and after the test. So, that is why if it is a weighing type of thing, then obviously when we put the water, we know what is the weight, and then after running the experiment for certain period of time, say 24 hours or so, we will know how much water has been lost, or how much weight loss has taken place. So, that we can convert that this much water has transpired through plants. And this method yields good results as long as natural environmental conditions are maintained. So, obviously, if you maintain the natural environmental conditions, that means the air and temperature conditions, they are similar to natural conditions, then obviously you will get a good estimation of or measurement of transpiration value using this method. Now, coming to evapotranspiration, there are several terms which are popularly used, and it is better to know or understand those terms. The first and foremost is potential evapotranspiration, which is known as PET, and this is defined as the amount of water that would be evaporated and transpired by a specific crop, soil or ecosystem if there were sufficient water available. So, that means if you have a system where a particular crop is growing, or a natural system, so let us say, and if water is not a limiting factor, then if sufficient water is available, then whatever evapotranspiration occurs, that is sum of evaporation and transpiration occurs from water bodies, soil as well as plants, then that is referred to as potential evapotranspiration. And because it is potential, that means that is the max possible under given environmental conditions, that is the max possible value of evapotranspiration. Then the second term comes is actual evapotranspiration, AET, which is the real amount of water lost through evaporation from soil and transpiration by plants in a specific area over a given period. So, obviously, as you can see that both definitions more or less are similar, except for in the case of PET, we are ensuring that there is a sufficient water availability, that water is not a limiting factor, but in this case no such guarantee is given, no such statement is there. So, it is a natural water, I mean you do not know how much water is available. So, under such circumstances, whatever evapotranspiration occurs, that is referred to as actual evapotranspiration, and obviously as you can guess, PET is always greater than AET. So, these are the two very common terms which are used, PET and AET, which you will find in textbooks or journal papers if you refer. Then another important term which is used is reference evapotranspiration, ET0 or ET0, where 0 or naught is used as suffix ET0 or ET0, reference evapotranspiration, which is defined as the rate of evapotranspiration from a standardized reference surface, typically short green grass, which serves as a benchmark to assess the water needs of various crops. So, obviously, because the evapotranspiration differs from one crop to the other, from one condition to the other. So, in order to standardize the evapotranspiration estimation, this reference evapotranspiration is defined, which is with reference to a typical reference crop, which is short green grass, which is used as a benchmark to assess the water requirements of various other crops. More specifically, the reference surface is a hypothetical grass reference crop with an assumed crop height of 0.12 meters, a fixed surface resistance of 70 second per meter, and albedo of 0.23. So, these are the specific conditions which are defined for the short green grass, which is used as a reference crop, and the reference surface closely resembles an extensive surface of green well watered grass of uniform height, actively growing and completely shedding the ground. So, that means it is assumed that this green grass it is being grown in a large area, and it is all other like water, nutrient, environmental condition and the growth factors, they are all ideal, and the growth is uniform and active, and it is completely sharing the ground. And two other values which are referred here is that a fixed reference surface reference resistance of 70 second per meter, which implies a moderately dry soil surface resulting from about a weekly irrigation frequency. So, if you have if in a particular field, if you follow a weekly irrigation schedule, then obviously at the end of the schedule, this is the typical surface resistance that will be available. And similarly, albedo is the proportion of incident radiation that is reflected by surface, and its value is 0.23. That means 23% of incident radiation is reflected in this condition while defining the reference evapotranspiration. Now, with reference to that, we have crop evapotranspiration ETC, that is crop evapotranspiration, which is defined as the water requirement of a specific crop under given environmental conditions. It includes both the water lost through transpiration by crop and water needed for soil evaporation. It is assumed that the crop is disease free, well fertilized, grown in large fields under optimum soil water conditions, and achieving full production under the given climatic conditions. So, first we talk about reference. Now, you instead of reference grass, if you put a typical crop, it could be wheat, maize, paddy, whatever, and then you grow under similar circumstances, that the ideal conditions for crop growth, then whatever evapotranspiration value you will get, that will be reflecting which will be giving a value of crop evapotranspiration ETC. So, ET0 and ET0 or ET0 and ETC, these are two, one is for reference, other is a particular crop. So, basically then we can say that we have a reference evapotranspiration ET0, which is for a reference crop under ideal conditions, and that simply means if these ideal conditions are all maintained, then ET0 depends on the climatic conditions only. Then we have next one is the crop evapotranspiration under standard conditions. So, if it is all standard conditions are made, that is well watered crop, optimal agronomic conditions, and then whatever we get for that particular crop, that is crop evapotranspiration, and this value can be obtained by multiplying this ET0, ET0, that is the reference crop, by a crop coefficient Kc factor, crop coefficient factor. So, that will be typical for a particular crop. Then another term which comes out is crop evapotranspiration under non-standard conditions. So, we saw that a crop could be grown under well watered crop optimal agronomic conditions, but in the natural condition may be slightly different, that there could be water and environmental stress, and in that case the evapotranspiration of crops grow under management in environmental conditions that differ from standard conditions. What happens that we call that as ETC adjusted, that crop evapotranspiration adjusted, and of course, we have to use Kc adjusted, and also we have to use Ks, which is referred to as stress or reduction coefficient, which accounts for non-standard conditions. So, obviously, if we ET0, if we multiply with Ks and Kc, then we will get the actual crop or adjusted crop evapotranspiration, which is for crops going under water and environmental stress. So, basically ET0 we can say it depends on weather parameters, ETC depends on crop characteristics, and ETC adjusted depends on additionally depends on management and environmental factors as well. Now, let us come to factors affecting evapotranspiration, and there are several factors which affect evapotranspiration. Some of the factors we have seen already while discussing evaporation. More or less similar factors remain here. So, say for example, temperature. Higher temperatures generally lead to increased evapotranspiration rates. Warmer air can hold more moisture, prompting faster evaporation. Similarly, higher temperatures can accelerate plant transpiration rate. So, we also saw that if there is a vapor pressure difference which also depends on water temperature and surrounding conditions. So, obviously, this is how temperature affects evapotranspiration. Then humidity, when the air is already saturated with moisture, there is less room for additional evaporation to occur. Low humidity levels encourage faster evaporation. So, if it is a humid condition, obviously the vapor pressure difference will be very, very low. That means evapotranspiration value will be low, but if the humidity is low, that means there is a larger difference between EW and EA, and larger evapotranspiration could occur. Wind speed, we already know wind helps replace moist air near the evaporating surface with dry air, allowing for increased evaporation. So, if wind speed is high, evaporation is large, that we already saw, and stronger winds can enhance evapotranspiration rates. So, obviously, when evaporation is more, evapotranspiration will be more. Solar radiation, solar energy drives the process by providing the heat necessary for evaporation and transpiration. Higher solar radiation intensity typically lead to increased evapotranspiration. So, if solar radiation or the heat necessary is heat is higher, then evaporation will be more, transpiration will be more. So, sum of evaporation and transpiration, that is evapotranspiration, it will also likely be more. Then, of course, the vegetation and plant characteristics, the type, size and density of vegetation impact transpiration rates. Plants with larger leaf areas and more open stomata generally transpire more water, and the stage of growth and health of vegetation also affects transpiration rate. So, if it is growth is more, and of course, if vegetation is healthy, then evapotranspiration will or transpiration losses will be more. Similarly, if the plants have larger leaf areas, so more stomata, that means more openings, more transpiration. Soil moisture, when soil moisture is high, evaporation is limited due to already saturated conditions. However, as soil dries out, evaporation rates increase. So, obviously, when soil moisture is high, the environmental conditions is more humid or moist, that means evaporation will be lower, but if it is relatively dry, then evaporation will be more. Climate weather patterns, dry and hot climates generally exhibit higher evapotranspiration compared to cooler or wetter climates. So, regions we already know, if it is hot, then obviously evaporation will be more, transpiration will be more, and the vice versa condition will be in cooler and wetter climates. Altitude, already we have seen that higher altitudes may experience lower atmospheric pressure and cooler temperatures, which can lower the evaporation and evapotranspiration rate. So, at higher altitudes, evapotranspiration will be lower, as was the case for evaporation. Now, coming to measurement of evapotranspiration, and typically evapotranspiration is measured using lysimeters or in-field plots. So, lysimeter studies involve growing crops in large containers, as you can see here. These are the containers put in the field. So, growing crops in these large containers and measuring the water losses and gains. ET can be estimated by determining the amount of water required to maintain constant soil moisture conditions within the tank container. So, typically these are weighing, there is a weighing facility. So, these are weighing type of lysimeters are generally preferred, they are put in the field, and a special watertight tank containing soil and position within a crop field is buried such that the soil level inside and outside the container is same. So, it is put in the field, exactly field where the similar crop and similar conditions are, a similar crop is being grown. So, it is buried in the sense that soil and plant conditions inside and outside are same, and they contain the same type of plants as those in the surrounding field, obviously. However, both the soil and vegetation in the lysimeter are hydrologically isolated from the surrounding soil. So, of course, as it is a metallic container. So, obviously, there is no exchange from the field and the soil or crop which is being grown inside the container, and they are designed to accurately replicate the soil conditions, moisture levels, type and size of vegetation found in the surrounding area. So, all conditions remaining same, and of course, they are weighing type, and so Basically, most of them have facility to measure various components of hydrological cycle, and thus they can very easily give us a value of evapotranspiration. Now, other than measurement, we can also estimate evapotranspiration, and two general approaches are used. One is by using catchment water balance, so which we have seen in almost all abstractions. So, equation which is preferred here is ET equals to P minus delta S minus Q minus D, which P is the precipitation, delta S is the change in the water stored within the catchment, Q is the stream flow, and D is the groundwater recharge. So, if we know precipitation, if we know change in the water storage, if we know discharge, if we know groundwater recharge, then we can estimate the value of VT from a given catchment. But besides water balance, there are several hydrometeorological equations which are used for estimating evapotranspiration, and some popular ones are here: Thornthwaite method, Blaney-Creedle method, Penman method, FAO 56 Penman-Monteith method, Hargreaves-Samani method, and the list can go on and on. There are more than 30 hydrometeorological equations that have been derived, and we will see only a limited ones, and we will discuss about these little bit here. So, first one, let us talk about Thornthwaite method. It is an empirical equation developed by Thornthwaite in 1948 to estimate monthly potential evapotranspiration. So, it gives potential evapotranspiration value, and the equation reads ET is equal to 2.54 K times F, where ET is PET in the crop season in centimeters, K is an empirical coefficient which depends on the type of crop and stage of growth, and F is sum of monthly consumptive use factors for the period, and F can be estimated using this relationship, that is sum of pH times TF bar divided by 100, where pH is monthly percent of annual daytime hours, which depends on the latitude of the place, and TF bar is the mean monthly temperature in Fahrenheit, in degree Fahrenheit. So, this is Thornthwaite equation, and we can use that for estimating evapotranspiration. Let us take an example. Estimate the potential evapotranspiration of area for a season November to February in which wheat is grown. Use crop factor of 0.65. So, for month November to February, monthly percentage of annual daytime hours are given here, and temperature is given here. So, using Thornthwaite method, this is the equation we know, and and the crop coefficient values are already given as K. These values are already known. So, obviously, what we need to do first is that, because the temperature used here is in degree F, so we have to convert these Celsius into Fahrenheit, and this is the relationship we know. If you remember, F minus 32 by 9 equals 2 by 5 C by 5. So, that is the relationship which is here. So, 9 by 5 times the Tc, that is temperature in degree C, plus 32 will give us the temperature in Fahrenheit. So, using this relationship, we can find out what is the temperature in different months, and also we can find out then the value of F, that is PS times TF divided by 100, and this, and of course, then sum of F comes out to be 16.91, and then ET, because we know K, we know F. So, K is 0.65, F is 16.91, and this is a constant anyway. So, this comes out to be 27.92 centimeters or 279.2 millimeters. So, the potential evapotranspiration of the area during the season is 279.2 millimeters. So, that is how we can use Thornthwaite formula to find out the evapotranspiration. Then the next method we consider is Blaney-Creedle method, which was originally developed by Blaney and Creedle in 1950, and the method calculates the reference crop evapotranspiration ET0 using the following equation. So, ET0 is P times 0.46 T mean plus 8, where ET0 is the reference crop evapotranspiration millimeter per day as an average for a month. T mean is the mean daily temperature degree C, which is average of maximum and minimum temperatures, and P is mean daily percentage of annual daytime hours, which is a function of latitude of the site, which a similar factor we saw it was also there in Thorndike equation. So, if we know the values of T mean and P, we can find out ET0 using Planck-Riedel. This method is simple as it requires measured temperature data only. However, the method is not accurate and provides only a rough estimate of evapotranspiration, especially under extreme climatic conditions. So, it has been found that in windy, dry, sunny areas, ET0 is underestimated up to 60%. And in calm, humid, clouded areas, ET0 is overestimated up to 40%. So, obviously, one has to use this Planck-Riedel method with a caution that it could underestimate or overestimate evapotranspiration depending upon the conditions under which you are using this method. Now, we come to Penman method, which is the classical form of Penman equation, which was first given in 1948 and then modified in 1963 to estimate potential evaporation from open water bodies or evapotranspiration is given by this relationship. As you can see, the Pen is potential evaporation or evapotranspiration millimeter per day, Rn is the net radiation at the surface, megajoules per square meter per day. Delta is the slope of the saturation water vapor pressure curve, kilopascals by degree C. Gamma is the psychrometric coefficient, kilopascal by degree C. K is the latent heat of vaporization, megajoules per kg. D is the vapor pressure deficit, EW minus EA in kilopascals, and Fu is the wind function, which is given by this relationship. Fu is a function of u, which is wind velocity or wind speed at 2 meters height in meter per second. So, obviously, as you can see, a large amount of data is needed in order to be able to Penman method, but its accuracy is definitely much higher than Planck-Riedel method or the Thorndike method we discussed, or in fact many other methods. And now let us come to FAO 56 Penman-Monteith method. FAO 56 Penman-Monteith method or equation was developed by Allen and others in 1998, and basically it is integral part of FAO irrigation drainage paper number 56, and it helps estimate daily reference evapotranspiration. As you can see here, the equation is more or less similar to, with little bit modifications of Penman method, and here two important changes are that here G, that is soil heat flux, megajoules per square meter per day is also considered, and rest of the things, rest of the variables are more or less same. So, here Rn is net radiation at the crop surface, T is the mean daily temperature, air temperature at height of 2 meters, U2 is wind speed at 2 height meters, Es is saturation vapor pressure, Ea is actual vapor pressure, delta is the slope of vapor pressure curve, and gamma is the psychrometric constant, kilopascal per degree C. Now, this equation is used, or this method is used as a global standard based on meteorological data. So, this is after a huge amount of experimentation conducted under Food and Agriculture Organization FAO by a team led by Richard Allen in 1998. They collected data from around the world and used this equation, and they found that this method works well in numerous locations if required data are available. So, it requires measurements of temperature, relative humidity, wind speed, solar radiation. So, the data demand is the main constraint on its use in locations where climate data are limited. Otherwise, if the data are available, then it gives the best estimate of evapotranspiration, and that is why it is referred to as a global standard based on the meteorological data recommended for use around the world. And this is the reference of this FAO irrigation and drainage paper 56, 1998, crop evapotranspiration guidelines for computing crop water requirements, and this is the site from which you can download this report, and it includes procedure for calculating ET0 and ETC from meteorological data and crop coefficient. So, all the required steps are given in this particular paper. Then lastly, we will discuss Hargreaves and Samani method, which was given by Hargreaves and Samani in 1985 to estimate daily reference evapotranspiration. And this equation is ET0 is 0.0023 Ra Td to the power 0.5 Tc plus 17.8, where Ra is the extraterrestrial radiation watt per square meter, Td is the maximum temperature minus minimum temperature, and Tc is the mean temperature. So, and Ra can be estimated for a particular location using this relationship, where Gc is the solar constant, which is approximately 1360 or 1361 watt per square meter, and N is the nth day of the year. So, for a location and for a given day of year, one can estimate this. And this method is simple and provides reliable estimates of ET0 and requires daily maximum and minimum air temperature data as the only input. And that is why this is very popularly used in several research studies, several models. However, there is a catch that this method is only applicable for crop growing season. So, theoretically it is not valid for the dormant season. So, if you are using this method in a continuous model, so one has to be a little careful, but as far as only the crop growing season is concerned, this gives a pretty good estimation of evapotranspiration with minimum data, and that has been shown by research around the world. So, with this we come to, after measurement, we come to study the application of ETC. Why do we study ETC, or why do determine ETC? So, knowledge of ETC helps us in determining the irrigation requirements, because knowing ETC, net irrigation requirement can be estimated using this relationship, that ET crop, that is the total water that is required by crop minus effective rainfall. So, if effective rainfall, that is rainfall minus losses. So, the difference in these two is net irrigation requirement. That means that much water is needed by the crop to meet its evapotranspiration requirement. And of course, if you consider the field water use efficiency, then the field irrigation requirement can also be estimated by taking that into account. So, FIR is NIR divided by the field water use efficiency. So, if we estimate ETC for a crop, then we can find out what will be the total field irrigation requirement. So, that is the practical application of evapotranspiration. So, with this we come to end of this lecture. Please feel free to give your feedback and also raise your questions in the forum, so that it can be answered. Thank you very much.